All right. Now we're going to start another topic, which is another type of machine called the push-down automata. And I must admit, the last few times I've taught this course, I just skipped push-down automatas totally because I think they're kind of dumb. But last year, Eric Rupert was doing something.
Why are you teaching it then?
I'm telling you now. I'm explaining why I'm teaching it. One, it's on the course curriculum, which is a good reason to teach it. And two, Eric wanted me to take over his class a couple times last year, and he wanted me to teach this. And so I busy made slides, and now I have slides for it. And so now that I have slides, we might as well cover it.
But is it difficult? Is it difficult and dumb, or is it easy and dumb?
It's about as, let's go with difficult and dumb.
Right.
And you said something about if the professor likes something, you better learn it because it will be in a test.
Exactly.
Does it work backwards if the professor doesn't like something?
Yeah, probably.
It's not on the test.
Probably.
Great.
But you didn't hear me say that. All right, so what's a stack?
It's recorded.
A stack, exactly. A stack here is you push on 1, 2, 3, 4, and then you pop off 4, 3, 2, 1. Right? That's a stack. And remember, we have Turing machines that have a read-write tape, and an NFA has a read-once tape. A push-down automata has a stack, has a read-once tape, and it has a stack. All right? And how does the machine go formally? Well, at each point in time, the push-down automata, it knows the current state that it's in, it knows the next character that's being read on the tape, and it knows the top character on the stack, and based on that, it chooses whether to push. It can push a string onto the stack, it can pop one thing off the stack, it can go to a new state. So that's what a push-down automata can do. And we're going to prove that what push-down automatas can generate is exactly the same things as context-free grammars. Yes?
So, push-down can pop off the stack too?
Yeah, you can pop things off the stack.
Does that happen simultaneously?
No, you either push or you pop.
How come you say it?
Why didn't I say pop? Well, because I made these slides today just as I was running to class with Eric Rupert's class, and I didn't say pop. Push or pop. It is called the push-down automata. It's not called the pop-up automata. All right. And context-free, and this push-down automata has to be non-deterministic, just like the context-free grammar is non-deterministic. All right, and we're going to prove that anything that context-free grammars can do is exactly the same thing as the things that these push-down automatas can do. So the first thing we're going to prove is, given a context-free grammar, we're going to make a push-down automata that does the same thing. And moreover, it occurred to me when I was making the slides that you don't even need states to do this. So it'll be a push-down automata with no states. So suppose the grammar goes to a bunch of things, and these could be terminals or non-terminals. Then there'll be a rule which says S is on the stack. You pop S on the stack, and you push the string onto the stack. And at any point, if the next character is an A, and your A is on the stack, then you can move past the character A, and you can pop A off the stack. So remember, this was our grammar we had before. Those are all the rules that are associated with it, right? You can this rule is you can pop the S and you push ABS, or you push BSA. I don't always say it a little dyslexically, but ASB, or you push BSA.
So you just add the rules of your contextual grammar, and then you add the two last rules that are pretty dumb.
Yep.
I mean, the two last
And then you're done.
you read that and you
Yeah.
pass it and you pop it.
Yeah. All right. So what we're gonna let's parse some string, and then we're gonna see how the machine does the same thing. All right. So you can go to that and go to that, and now there's this thing called the leftmost derivation, where you always replace the leftmost thing with first. So it replaces the leftmost S, then it replaces the leftmost S, it replaces the rightmost S, right? And then you get a string that's in the language. So what is the machine going to do? Our loop invariant is that the string that's written here, this string here, is always going to have some letters which have already been read from by this machine. They've already been scanned past the machine, plus the part of the plus what's on the stack. So right now nothing's been read, and S is on the stack. So then what do? You non-deterministically decide to use this rule. You're going to pop S, and you're going to push ASB. And then that's going to get us, so that's now on the stack. And then what's on the top of the stack is an A, and A is a terminal. So you're going to read A off the string, and you're going to pop the A off the stack. So we're going to use that rule, and we pop A off the stack, and we read the A. So now we've maintained the loop invariant that this string here is what's been read from the string plus what's on the stack. And then what are we going to do next? We're going to pop the S and replace it with SS.
So on the stack, is it S or just on the second line? When you had it before. Okay, or even this line now. What's on the stack right now?
What's underneath this thing? SSB.
Oh, okay.
And this has been read already. So then you pop the first S, and you pop the A and read the A, and you just kind of go like that. Does that kind of make sense? And then we're done. Everybody kind of buy that a little bit?
I'm just what's the past A mean? Is that you?
Well,
you're copying the one that you're on.
yeah, well, just like an NFA, it's reading these things. So if it sees an A, if an A is on the stack, so right now, A is on the top of the stack. So A is on the top of the stack, and the next character to be read is an A. So what the machine's going to do is move past the A that's on the string and pop the A off the stack. All right?
So, why this thing end when you remove all the S?
It ends when the stack is empty.
When you remove all the S, S is something that you don't know is there.
Yeah. Yeah. All right. So we should build at least one push-down automata for ourselves. So let's try. Can we build a push-down automata that has equal number of A's and equal number of B's? And what we're going to do is we're going to keep on the stack A's or B's. And if we've seen more A's than B's, then we'll have the excess B's on the stack. And if you have more B's than A's, then the excess B's will be on the stack. Yep. It will always have a finite number of things, but it will never get full. All right, so here's the rules, right? You start off, you read an A, and the stack is empty, so you push the A on the stack, and so you have one A on the stack. Yeah, the stack, as you get A's, we push the A's on the stack, and then when you get a B, since there's an A on the stack, and we got a B, then we pop an A off the stack. Right? And then you get more A's, and then you get B's, and it's just a way of counting the number of A's minus the number of B's. Right? Does that make sense? Yeah.
So when we reach to that line, we know that there are equal number of B's and A's.
Yeah, exactly. When the stack is empty, you know you see an equal number of A's and B's. Exactly. All right, so now we can also add states. So we could have the push-down automata also have what state it's in and move from state to state. And it just makes things more complicated. And so here it's just moving state to state. And the language is counting. It's doing exactly what it was doing before, but it's counting the number of the characters, the length of characters mod 3. Why? I don't know. I needed to do something.
For Q2, instead of using an empty string to go to an Q accept, why couldn't we just accept that Q2?
Q2 is another way.
Why didn't we go here? Just have that in accept state? I think that would have been fine too.
Between A and B and
I don't know why I did that.
read one.
Don't remember.
Q2 and it's not empty, so we don't have to accept Q2.
Yeah. I don't know. All right, so now we're given a push. This is a lot harder. See how much time we have left. We have 9 minutes left. Maybe we can actually do this in 9 minutes. All right, we're given a push-down automata, and we want to convert it into a grammar. All right? Everybody understand what we're doing? We have one of these crazy machines, and we can convert it into a grammar that generates the same thing. So here's some rules. First thing, if the rules are pushing lots of things, maybe it's popping something and it's pushing lots of things, then we only want it to do one thing at a time. Either it pops something or it pushes one thing. It doesn't push a lot of things. So what we're going to do is convert it so it remembers what it's doing with the states and it pushes one thing at a time. The other thing we're going to do is if the machine ever stops with stuff on the stack, it's going to empty the stack. So we know it's going to end with the stack empty. So this is plotting the height of the stack. When you're in the start, you're going to start in the start state and end in the accept state with the stack. We're going to start with the stack empty, and we're going to end with the stack empty. All right. So now what we're going to do is for every 2 states, if you have 2 states, there's going to be a rule which says there's going to be a non-terminal APQ, and what it's supposed to generate is any string that can be accepted by this machine starting in state P with the stack empty and ending in state Q with the stack empty is going to be generated by this APQ. So the start symbol, for example, is going to be AQ start to AQ accept, because that's what we want to accept. That's the things we want to, right? Starting in the start state ending in the except state. This is only going to take a few more minutes, everybody. Hold your breath. All right? So one thing that is generated from going from Q to Q, if you start in the state Q and end in state Q, one thing you could generate is nothing. You don't do anything during that time. Right? So that's kind of a base case. And also, one way to go from state Q with the stack empty to state Q, from P with the stack empty to Q with the stack empty, is to have a time in between which you're in state R with the stack empty. All right, so that's why we have a rule that what you can generate in going from P to Q is the same as what you can generate from P to R and from R to Q. You can concatenate those together. Similarly, this is a complicated one. If there's a rule that from P, state P, you read the character A and you push something on some U onto the stack, and then you go over to state R, right? Then later you happen to be in state S and you pop the U, right? Then you can figure out that this sort of thing works, right? Let's not sweat it too much. And so inductively, we're going to now prove that it all works. So if right, so if one of these, if a string can be generated from P to Q, then either it hits the 0 line or it doesn't, right? In which case, you either can use this kind of rule or use this kind of rule. And we just have one little example here, right? Here's a parsing, and you can go through and see how the parsing works. And I even remade these slides yesterday so that you would enjoy them so much more. But I think we've run out of enthusiasm and time. Any last questions about this? Here, let me just wait.
Computation classes, is it superior or